Okay, I think now we're good. Good afternoon, everyone. Today we're going to continue talking about how to calculate horizontal stress. And remember that this is something very important because our objective is to predict horizontal stresses in the subsurface that are going to be useful to tell us, among other things, what is the pressure needed for hydraulic fracturing. So what we did last time was to make assumptions of the tectonic stresses, and we said that we will derive these equations for a tectonically passive environment. With equations of elasticity and thanks to the Poisson ratio, we were able to come up with the equations that allow us to solve that are these equations. And now with these equations, we can tell what the effective horizontal stress is. Now that we have the effective horizontal stresses, the only thing that we need in order to get to total stress is just to add pore pressure to the effective horizontal stress. And that's it. That's everything you have to do. So let's see now, before we go to a more complex case, let's see how we derive from these equations the fracture gradient, something that probably you have heard a lot about it. And you will see that it comes right out of these equations very easily. All right, so remember, effective horizontal stresses, now we know how to calculate them. If you want the total stress, just add the pore pressure, and that's it. All right, so let's see how we derive the equations for fracture gradient. Let's imagine that we go to the Permian Basin, and in the Permian Basin, we want to know what is the pressure needed for fracturing. And on the top over here, we're going to connect a pump, and our objective is to increase the pressures so that we cause a hydraulic fracture here. Okay. So far, we have learned that we're going to have a pore pressure, which in this case, we're going to assume hydrostatic. Let me improve the zoom. The focus. OK, that's going to be the pore pressure. We have also a total vertical stress. And what we just learned with the previous equation is that the horizontal stress, the effective horizontal stress, is going to be a fraction of the effective horizontal stress. So if from here to here, this is the effective horizontal stress, vertical stress, that means that the effective horizontal stress is going to be a fraction of this. And if you remember when we plot here, when we put 0.25 for a Poisson ratio, the result was 1/3. And that's a number that I'd like you to remember very well. 1/3, and some other times we'll use the inverse of that, 3. So for a typical Poisson ratio, effective horizontal stress in a passive tectonic environment is going to be 1/3 of the effective vertical stress. So I divide this line in 1, 2, and 3, and this is going to be the value of the effective horizontal stress, 1/3 of the vertical, and the total horizontal stress is going to be a line that goes through that point, and it's to the left of the pore pressure, and it is at 1/3 of the distance. Let me change this a little bit to move it to avoid any confusion. This is the line of sigma V, and let me add some color too. This is going to be SH. I'm going to assume in this particular example, again, that this is a tectonically passive environment. Therefore, SH mean is equal to SH max, is just equal to SH, and SH is less than the vertical stress. Okay, so finally, we have the value of horizontal stress, and we know how to calculate it. All right, let's see how we derive from this the fracture gradient. Okay, SH, we said, is going to be the effective horizontal stress plus pore pressure, right? Again, this is total, and this is effective. All right, but from the equation that we derived last time, we know what sigma h is. And sigma h is going to be the coefficient of effective horizontal stress, which for linear elasticity is going to just depend on the Poisson ratio, if there are no tectonic strains, times the effective vertical stress, plus the pore pressure. And we also know what effective vertical stress is, because we know how to integrate well logs and calculate total vertical stress. And if we know pore pressure, we can calculate that effective vertical stress. So let's, if you see there is pore pressure over here, there is also pore pressure over here. So I'm going to take the effective vertical stress just in its own term, and the pore pressure here separately. And if I add these two things, this is going to be like this. I'm just doing math here, okay? It's just algebra. Okay. This value is the absolute value of horizontal stress. How do I do in order to compute the gradient? So remember, a gradient always is going to be a variation of stress or pressure with depth. And usually in petroleum engineering, when we refer to stresses, it's very common to talk about gradients, because the gradient is going to tell you what is the weight of the mud that you need to produce such a to reach such horizontal stress. So one thing is absolute values, and another thing is gradients. But let's now talk about gradients. If I want to do a gradient, what should I do? Take the derivative, right? Or if we do it in simpler terms, let's just say we'll take which is the same derivative or a variation with respect to depth, where depth is z. We know that the Poisson ratio for a specific location is not going to vary with depth. I mean, it's going to vary with depth, but for a specific location, it will not. And this is going to be delta C, and this is going to be delta PP delta C. But look at that. We already know these guys. You remember which these ones are? This is the gradient of total vertical stress that we said is how much, more or less? 1 psi per foot. And this one is the gradient of pore pressure, which in hydrostatic conditions is 0.44 psi per foot. And this one over here is the fracture gradient. Again, this is total vertical stress gradient. This is pore pressure gradient. And now this is the fracture gradient. All right. Small task for you. And the first one that tells me the answer gets extra points, okay? With these numbers, 1 and 0.44 and a Poisson ratio of 0.25. What is the fracture gradient? Let me check that the recording is going all right. It looks like it is. I'm going to pull up my sheet with your names. 0.63. Yes, that's the answer. 0.62, 0.63. And your name is? Buck Train. Okay, I found you. That's the answer, 0.63. So 0.63 then tells you that at the given location with these tectonically passive conditions that we have assumed, tectonically passive, which means that horizontal strains are 0, means that, say, at 1,000 feet of depth, the vertical stress is going to be 1,000, the pore pressure is going to be 440, and the horizontal stress is going to be 630. And 630 is going to be the minimum pressure required in bottom hole conditions to open a hydraulic fracture here. So the minimum pressure to open a hydraulic fracture in this case is going to be 630 psi if I say that this is 1,000 feet. We're going to see later on that in order to make a fracture and propagate a fracture, you need a little bit of a larger pressure. But the absolute minimum is going to be 630. That's to start talking. All right. Any question about this point? And this is very important. If you know this, if you know how to calculate pore pressure, if you know how to calculate vertical stress, if you know how to calculate horizontal stress, I would say that's 50% of geomechanics and what I want you to remember from this class. And this is a very important point. This is just one method to calculate horizontal stress. We're going to see other ones, but this is one of the main points of the class, to get to know about how to calculate horizontal stress for given conditions and what is the application for it. So again, any questions? Or we can make it now more complicated.
Would that basically be the same as your surface pressure?
Good question. No, this is not going to, this is the bottom hole pressure, right? But let's say that you have filled this wellbore with water with a mass density of 1 gram per centimeter cube. that means that just because of gravity in bottom hole conditions, you're going to have 440 psi already. So the additional pressure on surface that you need in order to get to 630 is this difference. That additional pressure is the one that you need on surface to make a fracture. But it will depend on the fluid, on the fracturing fluid and its density. We're going to see that later on when we get more in detail to fracturing. All right, so this is the easy case in which these two strains are 0. However, we have seen the equations that allow us to calculate stresses when this is not 0. And in order to do that, we need to come back to these equations. And now we're not going to make epsilon 1 and epsilon 2 equal to 0. We're just going to let them to not to be equal to 0. And still the shear strains, we're going to make them equal to 0. But now these three are not going to be equal to 0. And the result of that, there is no, we don't want to do all that math because it's going to take a long time. And you can see in my notes, but it's just math. It's going to give us the equations that I'm going to write right now. So now we are relaxing that condition of tectonically passive, and now it's not tectonically passive anymore. This happens in many locations where there is some tectonic activity, and because of that, if you have a plate which is, let's say, pushing these layers, and sometimes you could have mountain building in some locations. So this is a plate which is subducting into another plate, and it's making a mountain. Oh, sorry about that. So if you look from the surface, you will have a mountain here, and further away, you will have tectonic stresses. And those tectonic stresses are going to make the horizontal stress larger than in a tectonically passive environment. So in this case, now we're going to have a tectonic stress and strain that's going to go in this direction. Again, this is going to make some mountains over here, but further away, it's just going to add compression in this direction. And in this perpendicular direction, we're going to have the minimum horizontal stress. You may say, where does this happen? It happens in places close to convergent tectonic plates, like, for example, in Asia, close to, let me find this image, here, close to the Himalayas, over there, you see the mountains. There are some hydrocarbon producing basins over there that they have a significant tectonic strain. It occurs in Australia, occurs in South America, in Argentina, in Colombia, some other places in close to the Rockies. So this is something that we need to take into account. In some places, they may not be as extreme as causing a reverse faulting regime or an IMA or a strike faulting regime, but still you have to take it into account because the difference between horizontal stresses is something that's going to be very important, as we're going to see later on. Okay, so now I have these tectonic strains. And when I consider these tectonic strains, and let me add here a coordinate system, 1, 2, 3, 3, always we're going to put it in the vertical direction. If I use equations and I do a similar math to the one that we did before, we're going to get that the horizontal effective stress in direction 1 now is going to depend on the strain in direction 1, on the strain in direction 2, and of course on the overburden. Notice that this last term is the same as before. The same, the other horizontal stress is going to depend on the horizontal strains as well, and on the overburden. Overburden is always there, and the effective vertical stress is just equal to the integral of the weight minus the pore pressure. So with these three equations, now you can tell me what are the horizontal stress, even when these strains are not equal to 0. All right, in this particular case, this one is epsilon 1,1, and this one is epsilon 2,2. These two strains are called tectonic strains. Let's analyze what is the impact of those tectonic strains. Okay, first equation, sigma 1,1 in this direction. What this is telling me is that that stress is going to be proportional to the tectonic strain in this direction, and proportional now to the Young modulus divided 1 minus the Poisson ratio squared. This quantity is called the plane strain modulus. And I hope you remember that I told you that in geomechanics problems, usually we do not use Young modulus by itself, because in many applications we do not have unconfined conditions. And this is one example in which we need to combine the Young modulus with the Poisson ratio to give us the coefficient of proportionality between stress and strain. And in this case, it's called the plane strain modulus. Okay, so the stiffer the rock, the more stress you're going to have in this direction, and also it's going to depend on the stress in the perpendicular direction, but not as much as in the same direction. You see over here that there is a Poisson ratio. That means that if you were to push in direction perpendicular to direction 1, still because of the Poisson effect, you're going to have some reaction in direction 1, but that's going to depend on the Poisson ratio. This is the same thing as when we were pushing a material in one direction and then expands in the vertical direction. Well, in this case, it's the same. If you have a tectonic strain, say in this case north-south, it's going to compress in direction north-south, but also is going to make the rock try to expand in direction east-west, and as a reaction, you're going to get a stress in that direction. So you need to consider those two tectonic strains. And for sigma 2,2, it's very similar. In direction, there is a mistake here. Sorry about that. In direction 2, it's proportional directly to the plane strain modulus, and in direction 1, it's proportional to the plane strain modulus times the Poisson ratio, which is always like a 20% more or less of that. And always you're going to have here the overburden component. All right, So let's see an example of this. Let me show you an animation that's going to illustrate the effect of this. Okay, so these are the same equations that we have seen so far, and here we have the simplified version with the horizontal stresses instead of 1, 1, 1, 2 in terms of the max and the minimum. I'm going to write those, just give me a minute, but before I'm going to launch this animation, this is going to take some time. So I'm just going to copy in my page these equations 3.32 that you see over there. That is the same thing as the one that we have in terms of the other indices, but just written a little bit differently. Do you have any questions?
Yeah,
Yes.
so yeah, last time the effective stress and the vertical direction, we used an expression for in terms of the strain in that direction.
Yeah.
Why don't we use the same expression that we use now, which is the integral of density?
For which one? I didn't.
So for the vertical effective stress.
Yes.
On Monday when we had a confined, like we have a passive, tectonically passive environment. For the sigma 3,3.
Yes.
Expression in terms of the
Oh,
strain.
okay. I know what you mean. So let me tell you why in just a sec. We don't use strain for calculating the vertical effective stress because that one is usually an unknown. We don't know what that is. And just let me finish this equation. And let me switch to here. I think this is the equation that you mean, right?
Yeah.
So, okay, we don't use strain to calculate the effective stress because we don't know that. What we do know is the value of total stress, vertical stress, and we know pore pressure, so we get it directly from there. All right, so I just copied again the equations in terms of sigma h max, sigma h min, sigma b. And we're going to see an animation now of that. All right. Okay, so for those of you that like Python, you can find this script in my notes, and you can copy it, do everything. Yes?
For the plane strain modulus, why is the horizontal ratio squared?
You can see the math here in my notes, and it's just math in order to get to this expression, and it results from multiplying some of these terms that go in the equations. I cannot come up with any physical explanation of that, but when you do the math, that's what you end up with. You end up with the product of 1 minus Poisson ratio times 1 plus Poisson ratio, and that's the difference of squares, and that's how you get that. Okay? All right, so let's see. We're going to run this, and this is the result. All right. Now I have vertical stress and pore pressure. Notice that my Poisson ratio is equal to 0. A Poisson ratio equal to 0 would mean that there is no effective horizontal stress, which in reality doesn't happen. So let's put some realistic Poisson ratio here, like let's do the 0.25 that we talked about. But notice how it is increasing, right? The bigger the Poisson ratio, the bigger the horizontal stress. We said that some rocks tend to creep with time, and that sometimes you can interpret it as a large Poisson ratio that will also yield a high horizontal stress. But let me take it back to 0.25. All right. Now let's start adding the tectonic strains. If I add a tectonic strain direction 1, then S11 is going to increase. S22 will increase 2, but not as much as S11. Let's increase it a little bit more, and you may get, if S11 is too large, you may get to strike slip condition as you see right now. And if you increase it even more, you could get to reverse faulting, but we're going to have to increase also epsilon 22. So I increase now epsilon 22. Know how much it changes S22. S11 changes 2, but not as much as S22. And now we are in reverse conditions. Remember that these equations, and that's very important and something that I'm going to write in detail right now, they always give you effective stresses. So the first thing that you have to do is calculate pore pressure. And the last thing that you have to do is you have to add pore pressure in order to get total stress. Oh, this is wrong. This should be total. All right, so let's see what would be the effect of changing pore pressure. If you change pore pressure, which in this case I'm just changing it with adding some curvature, the effective stresses are going to change too. And let me bring this back to small tectonic strains. I'm going to add just a little bit in the other direction. Now I have a condition with overpressure, but notice that still the effective horizontal stress is 1/3 of the effective vertical stress. That condition still holds. And if I add a little bit of tectonic strain, then horizontal stresses are going to change. All right. I don't remember exactly what you have to do in the homework, but you have to do something similar to this, okay? All right, now with tectonic strains, then we are able to calculate what horizontal effective stresses are with depth. Remember that this one, you're going to get it from the density log. This one, you're going to get it from either, if you know that this is hydrostatic, or if you have a direct measurement, or from porosity, as you did in the homework. If you have an anomalous porosity, that could help you how to calculate pore pressure. Let's see how we get the other ones. The plane strain modulus and the Poisson ratio, you're going to get this from the sonic logs as a function of the slowness of the peak wave and the slowness of the shear wave. And also you may complement that with some laboratory tests. So it looks like we have everything, right? So same Poisson ratio comes from there. What are we missing? What we don't know for sure? Some mistake in here. What we don't know? The strains. We don't know the strains, right? We are building a model, but actually we don't know the strains. The two strains, the tectonic strains, going to be calibrated with field data. And that may come from a hydraulic fracture or from wellbore failure or from some other type of measurements. So what do I mean with calibrated with field data? That means that we're going to build this model and we're going to compare it to field measurements and adjust the values so that they allow us to predict or to explain what we see in hydraulic fracture tests or in wellbore failure. And these two things is what we're going to see later in the second part of the semester about how with geomechanics we can interpret hydraulic fracture measurements and wellbore failure measurements as a function of horizontal stresses. Okay, so let me finish with writing a general procedure to calculate total horizontal stress. And if you follow this recipe, you will see that it's simple and you will make no mistake. Let's go into a general case with some water and density of the rock that changes with depth. Okay, step number one. You remember what was the step number one? If you remember step number one, it's like 50% chance that you're going to get it right. What is the first thing that we calculate? What is the easiest calculation that we can do in geomechanics? Total vertical stress. So this is the first thing that you're going to calculate. If you have a well log, you're going to do it with a well log. If you don't have a well log, you just use typical gradients for total vertical stress. And if you need to consider water, you do consider water. That's just one additional level of complexity. But that's the first thing that you have to calculate. Second thing, you calculate pore pressure. Sometimes this could be hydrostatic, and some other times could be non-hydrostatic. If it's not hydrostatic, then either I'm going to give you the porosity that's going to allow you, and all the parameters that are going to allow you to calculate that non-hydrostatic pore pressure, or some other times I could just give you the parameter of overpressure that relates pore pressure to total vertical stress. So if you have this one and you have that one, you can tell right away what is the pore pressure. Okay, let me change the equation slightly so I make it clear. Pore pressure is going to be the parameter of overpressure times total vertical stress, where this is going to be given. In last semester, I had a couple of exams in which there was a common mistake that people were computing this at each depth, and they were considering this as a gradient. But don't do that. Always this parameter multiplies the SV at a given location. Okay? So if you have SV at 10,000 feet, then just multiply that SV at 10,000 feet times that number. All right. We have SV We have pore pressure. Third step, you get effective vertical stress, and that's an easy calculation, and it's like this. The fourth step, here it gets a little bit more interesting. Now we need to calculate sigma H max and sigma H min. How do we do this? We just saw one method in order to do that, which is isotropic elasticity. In that method, we saw two variations. A variation in which this is tectonically passive, and because of that, the equation of horizontal stress was very simple, and it was just Poisson ratio divided 1 minus Poisson ratio times the effective vertical stress, and we know we add that to pore pressure, and that's it. And then we saw the case in which we have tectonic strains which are not equal to 0. And in this case, you need to use these long equations that we wrote a few minutes ago. I'm not going to write again here, but you can do it. But you have the strains, you have the properties. You need a Young modulus in this case. In the first case, you just need a Poisson ratio, but now you need Young modulus and Poisson ratio. But you can do it. And this is what we learned just a little bit before. After we finish with elasticity, we're going to see another type of method which involves the failure of faults, or something which is called fault equilibrium. The idea here is that you can push with tectonic plates in horizontal directions, but that stress is not going to increase up forever. At some point, the rock is going to break, and when that breaks, that's when you get a fault. So there is a maximum value of the stress that you can put horizontally, and that's going to be limited by this. We're not getting there so far. Don't worry about this, but I just wanted to mention what you can do. And so let's call it A, B. And the last method is going to use the theory of viscoelasticity and consider the fact that you can compress rocks over a long time. But that doesn't mean that those stresses are going to hold. Stresses are going to relax with time. And also, when you apply a vertical stress, rocks also will tend to creep laterally, as we said in the case of salts or in the case of soft mud rocks, and that's going to increase the horizontal stress too. We haven't seen that yet, don't worry, but I wanted to mention these other two methods in here. But as soon as you get the effective horizontal stresses, now we can go to the last step, number 5, which is calculate the total horizontal stress. And this is just going to be to add the effective to the pore pressure that we already knew. And that's the end of the story. Total effective. We're going to see that in order to tell if the rock is going to fail in shear, we're going to need effective stresses. In order to tell if we can open a hydraulic fracture, we're going to need total stresses. So we need both, okay? We need both, and always we're going to calculate those two in order to use them in problems of geomechanics. Let me just add one more thing in here. So our objective is to understand the state of stress in the subsurface. Okay. Any question? If you apply this recipe again, it's always the same. And you're going to be able to solve those stresses. Let me check the homework to see. We're going to talk about the homework on Friday, but just let me check if I'm forgetting anything that you may need. I think the next thing is reservoir compressibility. And okay, we'll talk about this on Friday. Talk about this on Friday again. Okay, yeah. The last thing we need to talk about is reservoir compressibility. And this is just a problem about horizontal stress calculation with a given tectonic strain. All right, guys, yes?
When is this homework due?
When do you want it to be due? Monday? Yeah, Monday is good. Okay, but start working on it, remember? So Friday, the objective for Friday would be that you have the homework half done, and then just a few things that may probably you still need to see, then we'll talk about that. Guys, wait a minute, don't leave. I have 3 more minutes, and I want to introduce the next topic. All right, the last thing that we're going to see is an application of linear elasticity in order to predict reservoir compressibility. So for rock compressibility, this is the property of a rock to change in pore volume with a change of pore pressure. And usually in reservoir engineering, what you have to solve is the diffusivity equation, where this is permeability, viscosity, and this is total rock compressibility, and this is the variation of pressure in space. Here I'm just doing it in 1 dimension. And this is the value of total compressibility. The total compressibility is going to depend on the compressibility of the fluid and the saturations of the fluid. So saturation of gas, saturation of water, saturation of oil, plus the rock compressibility. And this is the one that we want to understand and we want to calculate. Okay, so while I do this drawing, can you tell me if it is good or bad to have a high rock compressibility when you are depleting a reservoir? So I'm going to be depleting this reservoir over here. I want you to tell me what is desirable. A high rock compressibility of a low rock compressibility. So this is going to be my rock. A high compressibility is going to be good because you can drain or you can push fluids more easily. But sometimes that can cause subsidence or deformations that may not be good for production. All right, guys, I'll see you on Friday.